MERT, a novel acoustic music understanding model, leverages large-scale self-supervised training to overcome instability in acoustic language model pre-training. This is achieved through the use of two teacher models: an acoustic teacher based on Residual Vector Quantisation Variational AutoEncoder, RVQ-VAE, and a musical teacher based on the Constant Q Transform, CQT. These teachers provide pseudo-labels for masked language modeling, MLM, style acoustic pre-training, allowing MERT to scale from 95M to 330M parameters. Experimental results demonstrate MERT's ability to generalize and perform well on 14 music understanding tasks, achieving state-of-the-art overall scores. This is a significant advancement, as MERT bridges the gap in music audio modeling, offering a general-purpose and cost-effective open-source model for music understanding tasks. By leveraging self-supervised training, MERT can be fine-tuned for specific tasks, making it a versatile tool for researchers and developers. The MERT pre-training framework offers a novel approach to general music understanding tasks, prioritizing efficiency and scalability. Building on the jukebox model, MERT replaces cumbersome transformer decoders with a Residual Vector Quantisation Variational AutoEncoder, RVQ-VAE, for acoustic representation learning and a Constant Q Transformation, CQT, model for musical representation. This multitask paradigm balances acoustic and musical representation learning, aiming to capture both pitched and tonal characteristics in music. By leveraging RVQ-VAE, MERT efficiently learns acoustic representations, while the CQT model extracts musically relevant features. This synergy enables the framework to excel in various music information retrieval tasks, including pitch detection, beat tracking, and source separation. Notably, MERT achieves state-of-the-art results in these tasks while being computationally more affordable than existing models. The framework's efficacy can be attributed to its ability to balance acoustic and musical representation learning, allowing it to effectively capture the complexities of music. By doing so, MERT demonstrates its potential to advance music understanding tasks, making it a valuable contribution to the field. In the realm of acoustic music information retrieval, challenges persist in developing open-source, generalizable, and lightweight learned representations that cater to both industrial and research applications. Existing acoustic music pre-trained models primarily focus on tagging tasks, relying heavily on supervised tagging labels for pre-training. Some studies have explored contrastive learning for acoustic music pre-training, but these efforts face limitations in terms of training data and model size. The connection between music and speech processing is profound, with potential benefits from adapting state-of-the-art, SOTA, speech pre-trained models for music audio processing tasks. Previous research has successfully applied self-supervised speech processing models to downstream music tasks, such as generating mono-piano music and music reconstruction. Audio representation with language modeling is a promising approach, leveraging mask strategy-based large-scale language models for acoustic music understanding. Hierarchical tokens have been generated for music reconstruction, and pre-trained VQ-VAE models have been used for speech representation learning with masked language modeling, MLM. The methodology section outlines the pre-training paradigm and architecture of the proposed models, employing prediction tasks to acoustic teachers, such as K-means or deep music features, and reconstruction tasks to music teachers, such as CQT spectrum, within the well-established masked language modeling, MLM, framework. A supervised learning setup is defined, where a labeled dataset is used to train the model, along with notation for the data samples and corresponding labels. The page delves into SSL methods, focusing on Hubert, which leverages offline clustering to obtain pseudo-labels. It highlights the challenges in reconstructing masked data for raw audio tasks and how Hubert addresses this by utilizing dimension-reduced features. The summary also details the loss functions used in Hubert, including the noise contrastive estimation, NCE, loss, and how it differs from traditional speech SSL methods. It emphasizes the need for better acoustic information modeling in music recordings, proposing two approaches based on traditional features and deep learning. The proposed method for extracting and representing musical information from audio signals employs two acoustic teachers. K means clustering and encodec, a learnable feature extractor. These tools capture timbre and pitch information in music by emphasizing pitch level information through a new reconstruction loss function based on the constant Q transform. CQT, spectrogram. The final loss function is a linear combination of the acoustic loss and the musical pitch loss. The evaluation protocol consists of 14 downstream tasks such as music tagging, key detection, genre classification, emotion score regression, instrument classification, pitch classification, vocal technique detection, singer identification, beat tracking, and source separation. These tasks are assessed using various datasets including N-Synth, Magnet Tag A-Tune, GTZ-AN, EMA Music, and MUSDB-18, among others. Evaluation metrics used include receiver operating characteristic, ROC, average precision, AP, accuracy, ACC, refined accuracy, ACC refined, coefficient of determination, R2 score, FM measure, F1, and source-to-distortion ratio, SDR. A detailed description of the datasets and tasks can be found in the appendix. The evaluation protocol adheres to the probing protocol, restricting fine-tuning and focusing on training a simple multi-layer perceptron, MLP, for frame-level tasks. To ensure a comprehensive evaluation, various pre-trained models from music and speech domains are selected as baselines. These include Music-In, CLMR, Mule, Jukebox, and JukeMir for music, and Hubert and Data2Vec for speech. To demonstrate the effectiveness of the pre-training paradigm, the speech models are retrained and denoted as Hubert Music and Data2Vec Music. During training, the self-supervised learning (SSL) architecture is deployed with matched data scales for model sizes, utilizing a large-scale music dataset and a special edition of the base model trained on a publicly available dataset. To manage computational complexity, a strategy of randomly truncating audio clips into 5-second segments is adopted. The model incorporates a convolutional relative positional embedding, enabling effective operation in longer contexts. Notably, scaling up acoustic encoder-only models results in training instability, leading to decreased performance and even crashes, despite attempts to mitigate these issues. Deep norm, a method aimed at stabilizing acoustic language model pre-training, has been found to be ineffective. However, incorporating attention relaxation techniques and transitioning from post-layer normalization to pre-layer normalization has proven beneficial. This refined approach significantly enhances the performance of MERT models on various downstream tasks. In tasks focusing on local-level musical information, MERT models showcase their strengths by providing competitive results. They are also competitive in tasks requiring global-level information, demonstrating their ability to adapt to different contexts. One notable aspect of these models is their good performance with limited data, indicating their capacity to learn generalizable music representations. The findings suggest that the refined approach can significantly improve the efficiency and effectiveness of acoustic language model pre-training. This could potentially revolutionize how we understand and process musical information, leading to more accurate and efficient music processing algorithms in the future. The MERT RVQ-VAE model is evaluated with parameter sizes of 95M and 330M, leveraging the encodec feature to scale up the dataset compared to K-means. Results show that increasing the model size to 330M yields improved or similar performance on most tasks, except for beat tracking, compared to the MERT 95M RVQ-VAE model. Notably, lightweight MERT models achieve better or comparable performance with only 1.9% and 6.6% parameters compared to the self-supervised baseline Jukebox 5B. This suggests that the MERT paradigm can efficiently scale up to larger models while maintaining performance. The authors investigate the effectiveness of acoustic and musical teachers in the MERT paradigm, exploring optimal combinations and selections of teacher models on a subset of downstream tasks, including auto-tagging, key detection, genre classification, and emotion recognition. Results demonstrate that the K-means acoustic teacher with additional chroma or CQT features, denoted as K-means logmol plus chroma and K-means MFCC plus CQT, significantly improves key detection ability and raises accuracy, while maintaining or increasing performances on other tasks. Furthermore, the authors observe that introducing extra pseudo-prediction targets in the masked language modeling scheme can better excavate the potentials of transformer models. This suggests that designing a proper multitask learning pre-training paradigm can guide the model to produce more general representations for various music information retrieval tasks. Researchers propose a novel paradigm for pre-training large music audio processing models using self-supervised learning, SSL, introducing the Music Encoding and Representation Transformer, MERT, model. MERT integrates Residual Vector Quantisation VQ-VAE, RVQ-VAE, and Constant Q Transform, CQT, teacher models, providing a unique blend of acoustic and musical information necessary for masked language modeling-based pre-training for music understanding. The MERT model is trained with in-batch noise mix-up data augmentation and pre-layer normalization, pre-LN, enabling the learning of robust music representations with further training stability. Evaluation results show that MERT surpasses previous SSL baselines, achieving state-of-the-art or comparable results across a wide range of music information retrieval tasks while using significantly smaller parameter sizes. A hyperparameter search is conducted to determine the optimal weight for the musical loss applied to masked audios in the k-means setting, with a weight of 1 yielding the best overall performance for the base model. However, when switching the acoustic teacher to RVQ-VAE, the models perform slightly worse on genre similarity than those with k-means. The study finds that leveraging only one top or bottom layer of the residual codebooks in RVQ-VAE provides substantial information in pre-training, and using all layers in the codebooks allows the student models to learn richer acoustic patterns. Randomly accessing one of the codebooks for each batch alleviates GPU memory usage and leads to similar performance compared to using all of them at once, but predicting 8 codebooks together is adopted for faster convergence in the finalized design. Despite being capable of handling longer sequences with relative positional embedding, the MERT models are limited by the short 5-second training context, and the approach could be further improved for tasks requiring understanding extended musical contexts if trained on longer sequences. The proposed model for music representation learning faces limitations and areas for future improvement. Notably, the models are currently trained on 5-second audio signals due to computational resource constraints, which may limit their performance in tasks requiring a comprehensive understanding of extended musical contexts. Future work involves training models on longer contexts once increased computing resources become available. Additionally, the authors encounter issues with gradient exploding during half-precision training for larger batch sizes and model sizes. Furthermore, an inverse scaling effect is observed when scaling up to 330 m, indicating that the design can be further improved by stabilizing the training process. The authors acknowledge the valuable advice of Anchao Yang and express gratitude for the support of various funding bodies, including the Department of Computer Science at the University of Manchester, UK, and the UKRI Centre for Doctoral Training in Artificial Intelligence and Music. This study highlights the need for continued refinement of the model design to address these challenges and overcome the limitations of current computational resources. Future work will focus on scaling up the model while maintaining training stability to achieve better performance in music representation learning tasks. Recent advances in music and speech processing have been driven by innovative research in audio-language modeling, neural audio synthesis, and speech representation learning. A seminal study by author et al. 2020 introduced a novel audio-language model, leveraging a transformer-based architecture to predict future audio sequences. This approach demonstrated improved performance in music generation tasks, outperforming traditional autoregressive models. Another significant contribution came from author et al. 2021, who proposed a neural audio synthesis method capable of generating high-quality audio samples from textual descriptions. This work built upon previous research in text-to-speech synthesis, extending its applicability to music and general audio signals. Furthermore, author et al. 2022 explored speech representation learning, developing a self-supervised framework for learning robust speech representations. This approach utilized a contrastive loss function, encouraging the model to learn discriminative features from unlabeled speech data. The resulting representations exhibited improved performance in downstream speech recognition tasks. These studies collectively demonstrate the potential of deep learning techniques in music and speech processing. Notably, they highlight the importance of audio-language modeling, neural audio synthesis, and speech representation learning in advancing the field. Future research directions may involve integrating these approaches to create more sophisticated music and speech processing systems. A key limitation of these studies is the reliance on large datasets, which can be challenging to obtain and annotate. Nevertheless, the findings presented in these papers pave the way for significant advances in music and speech processing. The realm of music information retrieval is a multifaceted field, encompassing various sub-disciplines such as tempo estimation and key detection. A seminal work in this area is 29, Nies et al., which introduced annotated datasets for tempo estimation and key detection in electronic dance music. This study significantly contributed to the advancement of research in this domain. Another notable contribution comes from 30, Korzeniowski and Widmer, who proposed an end-to-end musical key estimation method using convolutional neural networks. This approach leverages deep learning techniques to accurately identify the key of a musical piece, further expanding the capabilities of music information retrieval systems. These studies demonstrate the ongoing efforts to improve the precision and efficiency of music information retrieval algorithms. By utilizing annotated datasets and advanced machine learning models, researchers aim to enhance our understanding of musical structures and develop more sophisticated tools for analyzing and processing audio signals. The exploration of tempo estimation and key detection continues to be a vital part of this research field, as it enables the development of more accurate and efficient algorithms for music classification, recommendation, and generation. Furthermore, these advancements have implications beyond the realm of music, influencing various applications in signal processing and machine learning. In conclusion, the refinement of music information retrieval techniques through studies like 29, Nies et al. And 30, Korzeniowski and Widmer highlights the continuous evolution of this field. As researchers continue to explore new methodologies and technologies, we can expect further improvements in the accuracy and applicability of music information retrieval systems. Understanding the nuances of music, including timbre, pitch, and rhythm, is crucial for developing effective algorithms for tasks like music classification, generation, and source separation. Deep learning models, such as convolutional neural networks, CNNs, and transformer models, have been utilized for these tasks with promising results. Contrastive learning has also been shown to improve the quality of audio representations. Music-centric pre-training, which involves pre-training models on large datasets of music, has been effective in learning generalizable audio representations that can be fine-tuned for specific downstream tasks. This approach has been applied in various applications, including singing voice detection, music source separation, and audio generation. The development of new datasets and benchmarks is essential for advancing the field of audio research. For instance, the vocal set dataset for singing voice detection and the superb benchmark for speech processing tasks provide diverse and challenging data for training and evaluating models. Attention mechanisms in transformer models have also been employed for audio processing, allowing the model to selectively focus on different parts of the input sequence. This technique has been applied in various contexts, including music classification and audio generation. Despite the progress made, further research is needed to develop more robust and efficient models that can handle complex audio signals and tasks. Future directions may include integrating multimodal data into audio processing models to enhance their performance and versatility. The methodology section of the research paper introduces an innovative approach to robust representation learning in music signal processing, referred to as in-batch noise mix-up. This technique involves adding shorter audio excerpts to the original audio clip during pre-training, enhancing the learning of more robust musical representations. A pseudocode implementation of this technique is provided in Algorithm 1. A comparative evaluation of different pre-training settings is presented, including the size of the acoustic model, teacher model, target class, and loss weight. The results are displayed in Table 5, showcasing the model's performance on various tasks such as tagging, key detection, genre classification, and emotion recognition. The evaluation demonstrates that a proposed in-batch mix-up probability of 0.5 provides better performance for MERT RVQ-VAE, with a mix-up probability of 0.5 determined to be suitable based on average performance scores. The study also explores the use of different codebooks and their impact on the model's performance. The results indicate that using a 1024x8 codebook with an in-batch mix-up probability of 0.5 yields the best overall performance across various evaluation metrics. In conclusion, this section presents a novel approach to music signal processing by incorporating in-batch noise mix-up and evaluates its effectiveness through various pre-training settings. The findings suggest that the proposed methodology can significantly improve the robustness of musical representations and enhance the model's performance in different music-related tasks. The evaluation of the vanilla RVQ-VAE representation's effectiveness is presented in Table 6, showcasing the performances of the continuous representation from the encoder of the RVQ-VAE model. This supplementary analysis indicates that the vanilla continuous representations alone are insufficient for a robust music understanding baseline. The results demonstrate that the MERT pre-training brings significant benefits, enhancing the accuracy and precision in various music understanding tasks such as tagging, key detection, genre classification, and emotion recognition. The metrics include ROC, AP, ACC refined ACC, and R2V/R2AACC, highlighting the improvement in the model's performance after incorporating MERT pre-training. The Appendix B of the paper outlines the experiment's downstream tasks, including music tagging, key detection, genre classification, emotion score regression, instrument classification, and pitch classification. For music tagging, models are evaluated on Magna Tag Atune and MTG Gemendo datasets using macro average of ROCA UCs and average precision. Key detection predicts the tonal scale and dominant pitch level using the Giant Steps dataset. Genre classification estimates the most appropriate genre for each song using the GTZAN dataset. Emotion score regression predicts the arousal and valence of music clips from the Emmanouil dataset. Instrument classification identifies instruments in a given sound using the N-Synth and MTG instrument datasets. Pitch classification estimates the pitch category of audio segments from the N-Synth dataset. Vocal technique detection identifies singing techniques in audio clips from the vocal set dataset, each task with its specific metrics and datasets for comprehensive performance evaluation and comparison with baselines. The evaluation of a pre-trained model on various music information retrieval tasks is presented, including singer identification, beat tracking, and source separation. The vocal set dataset is utilized for singer identification, with a 12:8:5 training, validation, and testing split. For beat tracking, the GTZAN rhythm dataset is employed, with the model's performance evaluated using the F measure implemented in Miraval. In source separation, the MUSDB18 dataset is used, with the model's performance assessed by the source-to-distortion ratio, SDR. The authors investigate the generality and standardization of the framework by freezing the pre-trained model's parameters and utilizing it as a feature extractor for each downstream task. This approach enables a lightweight solution across different tasks, examining whether the representations are easily reusable. The pre-trained baseline model consists of a multi-layer perceptron, MLP, with one hidden layer, while a 3-layer long short-term memory, LSTM, network is employed as post-processing for source separation. Hyperparameter tuning is performed based on the Marble 2 benchmark, with a validation set designated for each task. The learning objectives vary across tasks, and if multiple evaluation metrics are used for the same task with a uniform dataset, they are evaluated separately. This approach allows for a comprehensive assessment of the pre-trained model's performance and adaptability across various MER tasks. Scaling up the MERT330M model under mixed precision training revealed training instability issues. To mitigate this, various configurations were explored, including pre-LN and post-LN settings, gradient clipping, and the attention relaxation trick. The efficacy of these approaches is demonstrated through training curves, showcasing the evolution of gradient norm, loss scale, and masked language modeling, MLM, losses on acoustic and musical targets. The pre-LN configuration, which applies layer normalization before the self-attention mechanism, exhibited improved stability compared to the post-LN setup. Gradient clipping, a technique that constrains the magnitude of gradients to prevent exploding gradients, also contributed to stabilizing the training process. The attention relaxation trick, which involves adding a regularization term to the attention weights, further enhanced stability. However, despite these efforts, training curves still exhibited fluctuations, particularly in the MLM loss on musical targets. This highlights the ongoing challenge of achieving stable training when scaling up language models. The presented results underscore the importance of carefully tuning hyperparameters and exploring novel approaches to stabilize the training process. The training curves provide valuable insights into the dynamics of the model during training, revealing the intricate interplay between gradient norm, loss scale, and MLM losses. These visualizations enable researchers to better understand the effects of different configurations and techniques on model stability, ultimately informing the development of more efficient and effective language models. Visualizing GTZAN representations with genre annotations reveals intriguing patterns for two selected checkpoints, MERT 95M public K means and MERT 330M RVQ-VAE. By utilizing the top 6 and top 8 transformer output layers, respectively, dimension reduction is achieved through uniform manifold approximation and projection (UMAP) on representations from the training set. The resulting visualizations, presented in figures 36, exhibit clustering according to genre information under different layer settings. Notably, representations from higher layers do not consistently demonstrate stronger genre-based clustering tendencies. This may be attributed to either genre not being the most abstract label for these music examples or the top transformer layers prioritizing masked language modeling, MLM, pre-training objectives. The visualizations of MERT 95M public K means layer 7 to 9 pre-trained representations showcase 10 genres: blues, classical, country, disco, hip-hop, jazz, metal, pop, reggae, and rock, across both validation and test sets. These visualizations provide valuable insight into the evolution of the model's internal representations of music genres across different transformer layers, highlighting potential areas for future exploration in understanding the relationship between music representation and genre classification. The MERT 95M public K means model's performance on the GTZAN dataset is analyzed, focusing on pre-trained representations from transformer layers 10 to 12. Visualized in Figure 4, the distribution of genres within the dataset across different layers reveals the model's ability to differentiate between genres. Layer 10 representations, shown in Figure 4a, exhibit clustering of genres such as blues, classical, country, disco, hip-hop, jazz, metal, pop, reggae, and rock in both validation and test sets. This indicates the model's capacity to distinguish between genres at this layer. Similar patterns of genre clustering are observed in layers 11 and 12, shown in figures 4b and 4c, respectively, suggesting the model maintains its ability to differentiate between genres across these layers. The K-means clustering approach in the MERT 95M public model enables visualization and analysis of pre-trained representations in the transformer layers. By examining these representations, researchers can gain insights into how the model processes and categorizes audio data from different genres. This study contributes to the understanding of transformer-based models in music classification tasks, highlighting their capacity to capture and differentiate various genres in the GTZAN dataset. The results inform future research on improving music classification models and their ability to generalize across different genres. Figure 5 presents a visualization of the pre-trained representations from layers 17 to 20 of the MERT 330M RVQ-VAE model on the GTZAN dataset. This model is a variant of the multimodal encoder transformer (MERT) architecture, integrating a multimodal variational autoencoder (MRVQ-VAE) to learn joint representations of audio and tags. The figure consists of 4 subplots, each illustrating the representations from a specific layer. The z-axis represents the validation set, and the y-axis represents the test set. The color-coded scatter plots show the distribution of the 10 genres in the GTZAN dataset, namely blues, classical, country, disco, hip-hop, jazz, metal, pop, reggae, and rock. These visualizations demonstrate the model's ability to capture genre-specific information in the higher layers of the transformer. Notably, the representations become increasingly discriminative, with the genres becoming more separable as the layer index increases. This suggests that the model is learning hierarchical representations of music, where lower layers capture general features and higher layers capture more specific, genre-related features. These findings are significant, as they imply that the MERT-330M RVQ-VAE model is capable of learning meaningful, high-level abstractions of music genres, which can be utilized for downstream tasks such as music classification, recommendation, and generation. The analysis of the MERT-330M RVQ-VAE model's performance on the GTZAN dataset focuses on its transformer layer representations from layer 21 to 24. The dataset includes various music genres such as blues, classical, country, disco, hip-hop, jazz, metal, pop, reggae, and rock. Visualizations of the pre-trained representations in these layers showcase distinct clustering patterns for each genre within the valid and test sets. Figure 6 illustrates the representations of GTZAN across layers 21 through 24, demonstrating the model's ability to differentiate between genres based on their unique characteristics. This highlights the model's effectiveness in capturing the nuances of different musical styles, contributing to the understanding of its performance on the GTZAN dataset. The appendix section of the paper delves into ethical considerations, underscoring the importance of adhering to ethical principles and guidelines. It emphasizes that no personal user information was utilized in experiments, instead leveraging open-access streaming services and open-source datasets for audio recordings. These recordings exhibit varying quality, with frequencies spanning from 16 kHz to 48 kHz. The authors of the paper underscore that their work has the potential to contribute positively to both social and scientific outcomes in the field of automatic music understanding.